Welcome travelers to Adventures in Security. In this video, we explore how to ensure we safely design, implement, and manage operational technology security. You can download the script for this video, including the bibliography, from the link below. Today we're going to look at operational technology, OT security, as a full life cycle. How we design it, implement it, monitor it, and manage it over time. We'll keep the examples grounded in the environments you see in the field. SCADA systems, PLCs and RTUs, industrial networks, and the growing edge of IoT and Industrial IoT devices. Here's the mindset I want you to take into the lesson. In OT, the crown jewels are usually not databases. They're physical outcomes, so availability, integrity, and safety matter as much as, and often more than, confidentiality. That doesn't mean we ignore confidentiality. It means we balance controls with reliability and safety constraints. We'll anchor the discussion on widely used guidance, NIST's Guide to Operational Technology, OT Security, the ISA/IEC 62443, Standards Family, and the NIST Cybersecurity Framework 2.0 for organizing program outcomes. By the end, you should be able to 1. Explain what makes OT security unique. 2. Design a segmented OT architecture. 3. Implement secure access and device controls for IoT/IIoT. And 4. Run monitoring and incident response without disrupting operations. Before we talk best practices, we need common vocabulary. OT refers to systems that monitor or control physical processes. Think motors, valves, pumps, robots, and the safety systems that keep people and equipment out of harm's way. SCADA is one OT architecture pattern. You have field devices like sensors and actuators, controllers such as PLCs or RTUs, communications links, and supervisory functions like HMIs and historians that operators use to see and control the process. Now, why isn't OT security just IT security with a different name? 3 big reasons. First, OT equipment often has long life cycles, decades. So you'll see legacy operating systems, old firmware, and industrial protocols that weren't built with authentication or encryption in mind. Second, the network traffic is frequently deterministic, and uptime requirements are strict. Just reboot or just patch can be unacceptable. Third, the environment blends cyber and physical risk. A bad change can stop production, damage equipment, or create a safety incident. IoT and IIoT add a twist. They expand the number of connected devices and data flows, often bridging plant floors to enterprise networks and cloud services. That can be great for efficiency, but it widens the attack surface, so design and governance have to keep up. Let's look at what we're defending against. In OT environments, many incidents start with familiar tactics: phishing, stolen credentials, exposed remote services, but the consequences can be very different. If an attacker reaches the OT layer, they may be able to change set points, disrupt alarms, inhibit safety responses, or cause process shutdowns. That's why the security goal is not only keep attackers out, but also limit what they can do if they get in. Government and industry advisories consistently highlight remote access and external connectivity as major risk multipliers. The more pathways into the environment, vendor VPNs, remote desktop tools, cellular modems, cloud connectors, the more carefully we must control identity, authorization, and monitoring. Another theme is the IT/OT convergence problem. Modern plants incorporate common IT components, but they may not be maintained with the same patching, logging, and asset management rigor as corporate systems. Attackers exploit that gap. So the takeaway for this slide is simple. Treat OT security as risk reduction for physical operations. We prioritize high-impact pathways first, remote access, segmented architectures, and visibility, because those controls buy you time and prevent small compromises from becoming plant-wide events. Now we organize the work. A best practice program is risk-based and lifecycle-based. Risk-based means we don't apply controls as a checklist. We tailor them to the process criticality, safety hazards, and business impact. Lifecycle-based means we plan security from design through operations, not as a bolt-on after commissioning. A practical way to structure this is the NIST Cybersecurity Framework 2.0. It gives you outcomes across 6 functions, starting with govern, so you can connect technical work to leadership decisions, risk appetite, and accountability. Then, for OT-specific detail, NIST SP 800-82R3 provides guidance and an OT-tailored overlay for security controls based on NIST SP 800-53. In other words, it helps you translate control requirements into what's realistic for OT. Finally, ISA/IEC 62443 is the standards many OT organizations use to define requirements across the lifecycle. Asset owners, system integrators, and product suppliers. You'll hear terms like zones and conduits, security levels, and secure development lifecycle, and we'll use those concepts throughout the rest of the lesson. If you remember one thing, pick a framework to organize outcomes, then apply OT-specific guidance and standards to implement them consistently. The first engineering step in OT security is knowing what exists. You can't protect, monitor, or recover what you haven't identified, so we build an OT asset inventory and a network/system map. In OT, discovery needs to be gentle. Passive methods. Listening to network traffic, reading configuration management databases, pulling data from controllers and historians often work better than aggressive scans that can disrupt fragile devices. Your inventory should include device type and role, firmware/OS versions, network addresses, communication paths, and, crucially, process criticality. A PLC controlling a safety-related function is not the same as a temperature sensor feeding a dashboard. Next, map data flows. Where does control traffic travel? Where does IIoT telemetry go? What connections exist between IT and OT, file shares, remote desktops, historian replication, cloud gateways? These diagrams become your source of truth for segmentation design, firewall rules, and incident response decisions. Finally, establish baselines. In OT, stability is an advantage. Many systems have predictable traffic and configurations. When you document normal, you make it possible to detect abnormal behavior later, and you reduce accidental outages caused by undocumented changes. With the map in hand, we design the architecture. The core best practice here is segmentation. Build zones with clear trust boundaries and tightly control the conduits, the permitted communications between them. A common mental model is the Purdue-style layered architecture. Enterprise IT at the top, a demilitarized zone, DMZ, as a buffer, and control networks and field devices deeper in. The specific layout varies, but the principle is consistent. Minimize direct IT to control connectivity, and force cross-boundary traffic through controlled choke points. From the ISA/IEC 62443 perspective, you define security zones based on function and risk, like safety systems, control systems, engineering workstations, and IIoT gateways, and then you define conduits with explicit security requirements. Practically, this becomes firewall policies, protocol gateways, and sometimes one-way data transfer, where you only need monitoring data going out. Segmentation supports defense in depth. Even if an attacker compromises one zone, lateral movement becomes hard, noisy, and containable. And as a bonus, segmentation also improves reliability by reducing blast radius when something misbehaves. Design tip: start with deny by default, then add only the specific protocols, ports, and destinations the process truly needs. Next, let's talk identity and access, especially remote access. because it's both essential and risky in OT. Best practice number 1 is least privilege. Every account, role, and credential should be limited to what that job function needs for the minimum time needed. In OT, we also care about who, what, where, and when, who is connecting, what device they're using, where they're coming from, and when they're allowed. For remote connectivity, avoid direct VPN to PLC designs. Instead, use controlled entry points such as jump servers or bastion hosts in an OTDMZ with strong authentication like MFA. Treat vendor access as a special case. Require approval workflows, time-bound access, and full session logging so you can review what changed. This is also where Zero Trust ideas help. The Zero Trust principle is that network location alone should not grant trust. You still authenticate and authorize before a session is established. In OT, we often implement this pragmatically. Strong identity, segmentation, and continuous verification for remote sessions. Finally, don't forget break glass access for emergencies. Just make sure it's monitored, documented, and rotated. Availability matters, but unmanaged access paths become permanent backdoors. Hardening is where we turn design into device-level reality. Think of hardening as creating a safe, repeatable baseline configuration for each class of OT asset. Servers, HMIs, engineering workstations, controllers, and IIoT gateways. Start with the basics. Remove or disable unused services and ports, enforce strong authentication where the device supports it, and eliminate shared/default passwords. For Windows or Linux-based OT servers, standard security baselines help, but you must validate changes against vendor support and operational constraints. A particularly strong OT control is application allow listing on critical workstations and servers. In many plants, software sets are stable, so allow listing can block a large class of malware without requiring constant signature updates. Also, secure your engineering workstation environment. The engineering workstation often has the keys to the kingdom. Logic downloads, configuration changes, firmware updates, so it deserves stricter controls, separate accounts, and careful USB and removable media policies. And remember physical security. Locked cabinets, controlled ports, and protected network drops. In OT, a physical connection can be the fastest path around your cyber controls. Hardening isn't glamorous, but it reduces routine risk and makes monitoring signals more trustworthy because normal is consistent. Patch and vulnerability management in OT is a balancing act. We patch to reduce known risk, but we can't create unplanned downtime or unsafe behavior. So the best practice is a structured, risk-based process. First, you track vulnerabilities and patches that apply to your environment, operating systems, firmware, industrial applications, and even embedded components. Then you prioritize based on exposure and impact. Internet-facing or remotely reachable systems usually rise to the top, as do issues that enable remote code execution or privilege escalation. Second, you test. OT patching should happen in a lab or staging environment that mirrors production as closely as possible. If you can't fully replicate production, you at least validate the patch on a representative device and confirm vendor compatibility. Third, you plan deployment windows and rollback. That means backups of configurations, controller programs, and system images. And when patching is not feasible because the device is too fragile, out of support, or safety critical, you apply compensating controls. Segmentation, strict access control, allow listing and monitoring. The goal is not patch everything immediately. The goal is reduce risks safely and predictably, and to document why certain risks are accepted and how they're mitigated. Now let's zoom into IoT and IIoT, because the device scale and diversity can overwhelm traditional OT practices if you don't set requirements up front. NIST describes a practical approach. Define the cybersecurity capabilities you expect from the device and the responsibilities you expect from the manufacturer or service provider. For example, at a minimum, you want unique device identity, secure configuration, protected data, secure update mechanisms, and a way to log or report security-relevant events. When you're procuring IIoT devices, translate those expectations into requirements. No hard-coded passwords, support for secure onboarding, signed firmware, a documented vulnerability disclosure process, and the ability to patch in a supported way. If the device can't meet those requirements, treat it as high risk and contain it with network controls. Operationally, build an onboarding/offboarding workflow. That includes provisioning certificates or credentials, assigning the device to the right network zone, and recording it in your inventory. When the device is retired or replaced, you revoke credentials and securely wipe sensitive data. Finally, remember that IIoT often sends telemetry to cloud platforms. Make sure you understand what data leaves the plant, how it's protected in transit, and how access to that data is controlled. Data governance is a security control too. If you can't see it, you can't defend it. Monitoring in OT has two goals: visibility for engineering operations and detection for cybersecurity. Because OT networks can be sensitive, many organizations start with passive network monitoring. Sensors that listen to traffic and build an asset and communication picture without actively probing devices. From there, you build detection around baselines. OT communications are often repetitive and predictable, so deviations, new talkers, new protocols, unusual command sequences, configuration downloads at odd times are meaningful signals. To make detections actionable, connect them to an attacker model. The MITRE ATT&CK matrix for ICS provides a common language for tactics and techniques in industrial environments. You can map your alerts to those techniques and build playbooks. If we see unauthorized program download, do these checks. If we see a new remote service, isolate this zone, and so on. Also integrate OT monitoring with your SOC, but respect operational context. Your analysts need process-aware escalation paths so they don't accidentally trigger shutdowns. The ICS monitoring technology guidance emphasizes evaluating monitoring approaches and trade-offs in industrial environments. Bottom line: monitoring isn't just buying a tool. It's building baselines, detections, and response workflows that fit how your plant actually runs. Incident response in OT must be safety first and operations aware. The classic instinct in IT, pull the plug, can be dangerous if it interrupts a critical process or disables safety functions. So we plan OT incident response with engineering, safety, and operations at the table. NIST incident response guidance emphasizes integrating response into broader risk management. And in OT, that means having predefined decision points. When do we isolate a zone? When do we fail over to manual operations? When do we involve the vendor? And what evidence do we collect? Build playbooks for the scenarios you're most likely to face. Ransomware on the OT Windows domain, compromised remote access credentials, a suspicious logic change on a PLC, or unexpected firmware updates. For each playbook, define detection triggers, immediate containment actions, safety checks, communications, and recovery steps. Recovery depends on backups that are actually usable. For OT, that includes controller programs, configuration files, historian data where needed, and gold images for critical servers. Store backups offline or in a way that ransomware can't encrypt them, and practice restores during maintenance windows. Finally, run tabletop exercises. The goal is to reduce panic. When an incident happens at 2 a.m., Your team should be following a rehearsed script, not inventing one. Supply chain and vendor management are huge in OT because you rarely build the whole stack yourself. You depend on OEMs, integrators, remote support tools, and managed service providers, so their practices become part of your risk. Start by setting security requirements for suppliers. ISA/IEC 62443 encourages lifecycle thinking across stakeholders, including secure development practices for products and requirements for service providers. Translate that into procurement language. Patch support commitments, secure update mechanisms, logging capabilities, and documentation of security features and limitations. Then apply cybersecurity supply chain risk management. NIST TSP 800-161 provides structured practices for identifying, assessing, and mitigating supply chain risk, things like counterfeit components, malicious functionality, and poor development or manufacturing practices. Operationally, control the vendor touchpoints. Remote access should be time-bound and monitored. Software and firmware updates should be validated and staged. If possible, request a software bill of materials, SBOM, or at least component transparency, so you can understand exposure when new vulnerabilities are disclosed. Finally, plan for end of life. Unsupported operating systems and controllers are common. When you can't replace them quickly, you need compensating controls, segmentation, strict access control, and monitoring, plus a roadmap for modernization. Technology controls only stick if governance and culture support them. This is where the NIST Cybersecurity Framework 2.0 govern function is helpful. It forces us to define who is accountable, what the risk tolerance is, and how decisions are made. In practical terms, governance in OT security includes clear roles and responsibilities between IT, OT engineering, and operations, change management that covers both cyber and process risk, and policies for remote access, removable media, and vendor engagement. Training matters too. OT operators need to recognize suspicious behavior and know how to escalate it. Security analysts need enough OT context to avoid false alarms and dangerous recommendations. Cross-training reduces friction and improves response time. Then we measure. Pick a few metrics that reflect real risk reduction: percentage of OT assets inventoried, number of unmanaged remote access paths eliminated, time to detect and contain anomalous behavior, backup restore success rate, and patching coverage for externally exposed systems. Finally, treat this as continuous improvement. Use assessments, audits, and post-incident reviews to update baselines, playbooks, and architecture. The goal isn't perfection, it's measurable maturity over time. Let's wrap up with a quick checklist you can apply immediately. First, inventory and map your OT and IIoT assets, including data flows to IT and cloud. Second, segment the environment into zones and tightly controlled conduits, especially across the IT/OT boundary. Third, lock down identity and remote access with least privilege, MFA, jump hosts, and session logging. Fourth, harden and maintain systems with safe patching. Allow listing where appropriate and reliable backups of configurations and controller logic. Fifth, build monitoring and incident response that's OT aware. Baseline normal behavior, train the SOC, and rehearse recovery. If you're building a program from scratch, start with the highest risk pathways, remote access and IT/OT connectivity. Those are the places where small mistakes turn into big incidents. In the description, I've included a bibliography of key guidance documents, NIST, ISA/IEC 62443 overviews, and incident response references, so you can go deeper on any area we discussed. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.